afternoon. So today we are going to start with the discussion of the equation that we just derived in the last class. So what we obtained was an equation for the evolution, right, of the conditional probability of finding a particle Lx comma t given that it started at y comma t prime. And what we derived at the end, so just to recall, we started with some assumptions on the probability distribution of small steps, right? So when t is close to t prime and x is close to y, that's what we mean by a small step forward. And for that distribution, we made certain assumptions, namely that it's for large steps, the probability decays sufficiently rapidly so that the rate of taking big jumps is 0. Therefore, the process can be continuous. And then we said that the first moment of the small step is finite and in general can be some advective speed. The second moment also exists and it's what we will call diffusion. And higher moments we showed after that automatically are 0, right, within these assumptions. And just using that by considering the evolution of the mean of some arbitrary function defined on the probability space, right, we could use some standard steps, right, and finally derive an evolution equation for this quantity. Okay? And that had the following form. Right? So of course, there we ended up with the equation in terms of z, right? Here I'm writing x, that doesn't matter. What's important is that y is fixed, right? That's where you started, right? And here the variable is x, right? This where you have gone. And so this gives you an evolution equation for the PDF of finding the particle at some time x in the future. Okay, so now I want to discuss a couple of things about what can we do with this equation, right? So the first thing is it's a PDE. And so if we want to solve this PDE, obviously, what do we need? So we've derived a partial differential equation now. It tells us what is the probability distribution given that I'm starting at a single point y. How will this distribution evolve? So to keep in, suppose this is y, right, at some time t prime. And then I'm at some later time t, right, where this is what I'm calling x, the coordinate. Now, if I look at individual trajectories, I have maybe 1,000 trajectories here, and it's following some stochastic evolution, right? This guy will go somewhere there. And in this manner, I'll have many trajectories, right? So I will then get some distribution of probabilities starting from here to go there. And this directly gives me the PDF at any point of time. Okay? So if I want to find the distribution, or again, think of it in terms of trajectories. If I start with 1,000 independent trajectories here, I evolve them forward in some fashion, some probabilistic stochastic process is involved in how they are propagating. And then I look at time t, they are spread out, right, along the x coordinate. And I want to construct the concentration field, if you like, that's the same as the probability distribution. Okay? So I don't have to do these 1,000 trajectories or whatever, right? I can directly get it by just solving this PDE. But I then need to solve the PDE, right? So let's say maybe sometimes you can get an analytical solution, but maybe you can always do it numerically. But what would I need to solve this equation? It's a standard PDE, right? So from PDE theory, what other information do you need to be able to solve it? Right, I need boundary conditions. Okay, so that of course depends on the problem. So for example, if I have a particle and I'm in an unbounded domain, right, then and if there's an analytical solution, I can always say the probability should decay to 0 far away because I know that if I start at y and in finite time, I will not reach infinitely far, right? So at some distance, the probability will go to 0. So I can just say it should decay. But if I'm doing a numerical solution, then that's a little tricky. I cannot do anything exact, but I can approximate, right? So I can take a big box, big simulation domain, and I can say at the ends, either the derivative is 0 or the probability itself is 0. Better to put the derivative 0. And then you should make sure that when you actually do the simulation in the time interval of interest, there is no probability reaching at your wall, right? Because the simulation box is artificial, the boundaries. So these are exactly the issues that you'll have to take up in your second assignment, right, when you try to solve it. So fine, so I can always specify some boundary condition. In some other problems, the particle may actually be diffusing in an actual box, in which case it cannot leave from the sides. So then I can impose some kind of no flux condition that particles cannot leave. That's again, how to impose that we will see in the assignment. So that I can do. What else do I need? Apart from boundary conditions, 2 boundary conditions, because I have the second order thing. I need an initial condition, right? So what should be the initial condition? Right, so that is inherent in the definition of this quantity, right? There is no choice. What should be the initial condition? Right, I know that initial condition should be such that the probability exists only at y, right? Everywhere else it's 0. At the same time, I know the integral of that probability should always be 1, right? So obviously the initial condition, so we'll say boundary conditions, right, is basically as per the problem, right, of interest. So that can vary from problem to problem, right? But the initial condition is simply that this quantity because I'm looking at z at t when t is t prime, that is the starting point, right? Given that I'm at y t prime, the only probability exists when z is equal to y, right? So it's a Dirac delta function, which is the spike at z equal to y, 0 elsewhere, and the integral by definition is 1. Okay. So this initial condition is fixed for this Fokker-Planck equation by the very definition of the PDF that we are considering, okay, because I've assumed that I'm starting at y. So that is the only initial condition I can have. So it's like saying if I solve this equation, I'm starting with this Dirac delta spike and I'm seeing how it is evolving. Right? In the special case, which we'll discuss more later, of A and B, of A being 0, let's say, and B being a constant, then I have the usual diffusion equation. Okay? And you already know from your mass transfer studies, right? The B will come out, so it will really look like standard diffusion, and this Dirac delta will spread out like a Gaussian. So that picture you can have in your mind. But in general, A can exist and B can exist. They can both be functions of X, so that Dirac delta can evolve in strange ways. If A is non-zero, the whole population will drift, right? If the diffusion coefficient depends on X location, then some places it will not spread, some places it will spread very fast. So all kinds of strange things can happen. Okay. All right, so that's fine, but you may be a little uncomfortable with this because it's quite restrictive, right? What you have found an evolution equation, but this only applies for this particular kind of situation where I'm starting all particles from a given position. But what we may very often be more interested in is to say, okay, I have, let's take the example of particles in a box, right? I have a bunch of particles and they are somehow spread out in my box. Maybe they are uniformly distributed, maybe they are localized but not all at the same point, or however I feel like initially distributing them, that I can put 2 piles of particles and leave them. Right? So all kinds of situations can arise. And then you want to see at some later time what is their distribution. Okay? So in this kind of setting, I'm not so much interested in starting at a particular location, all my particles. Rather, I'm spread out in some distribution. They will all diffuse all over and give me some new distribution. So in other words, we're asking how can I get an equation directly just for P of x comma t, not conditioned on being at any particular location. So it's like going backward the way we started our discussion. Remember in the beginning of talking about stochastic processes, I said this kind of PDF, if you look at just the distribution at some time, is a relatively, I mean, it's kind of an average quantity. What we really need is the trajectories. So finally, we've got an evolution equation for a particular trajectory, starting at y and going somewhere. But now we want to kind of use that information, which is more specific, to get the more general distribution, not for given initial locations. But already you can see that this somehow has more information. I should be able to use this to construct that. And this is where the nice thing about working with the Fokker-Planck equation comes in that the Fokker-Planck equation is just a linear PDE. Right? So all your PDE theory of deterministic systems or field theory can be applied directly, right, to this problem. So if you remember, if you've done a course in PDE theory, do you see how I can solve the problem? So what I'm saying is I want an equation right? Just the distribution, not conditioned on being at any particular place, right? And let's say I'm given that I've given some initial condition, okay? So phi of x is some initial distribution of particles, and I want to see how that distribution evolves. So if I want to solve this problem or get a PDE for this P, right, which will solve this problem, can I get it from here? Can I figure out what equation P will solve? Or can I calculate P using this Fokker-Planck equation? Does anybody have any idea? So if you've done PDE theory, solution of linear PDEs, then this is actually a standard problem. So what you should need to recognize is this is nothing but the Green's function to that problem. Okay, so I don't have the PDE yet, but you can really see this is like a Green's function setup, right? So the Green's function is nothing but if I have a linear PDE with some arbitrary forcing term, arbitrary initial condition, one way to solve this is to look for the fundamental solution, which is the solution to having an impulse source or an impulse forcing, okay, impulse initial condition. And then I can construct a general distribution by summing up impulses, okay, because it's linear. I can use superposition. So it's like saying I know that if I have a Dirac delta at y, like a spike at y, I know how it evolves. So now if I take spikes of different strengths and do an integral over all of them, I should get the general distribution. Okay. So formally, a way to see this right, is to write my solution P in terms of this, right? Right, so it is nothing but so I know how it will evolve given a y, okay, and then I know what all y's I also have, right? The initial y's are going to be distributed, right? Okay, that is just from superposition. So I know the solution for an impulse at a particular y. Then I can move that y around, I'll get different solutions. If I add them all up and weight it by the distribution of those impulses at t0, I should get the solution that I want, right? So it's just superposition. You'll immediately recognize it if you think of it as a heat transport problem, right? You put a heat source here, and then you have some temperature distribution. Now imagine I have two heat sources. The distribution will be the sum of those two solutions, right? And if I have a distribution of heat sources, I have to just do this integral, okay? And now you can see that that's going to be easy because all I need to do is, if I look at this equation, which is for this quantity, right? I can just multiply this equation throughout by phi of y. So let me call it 1. So I multiply 1 by phi of y, and I perform the integral dy, right? But y is an independent coordinate here. So I can multiply by y, take it inside, do the integral, take the integral inside. Right, and this P will just switch to that P. Okay, so I'll get exactly the same equation. Right? Okay, but with the initial condition that I want. So it's the same equation, I don't rewrite it. So in other words, this same equation, right, that I solve with the initial condition of a Dirac delta, right, is the problem I need to calculate the evolution of this condition PDF, given that I started y. Okay, the same Fokker-Planck equation, if I simply just change the initial condition to whatever initial distribution I have, will give me the evolution of the distribution at any time t without being conditioned. Okay, so that's what I wanted to see. So by deriving this, we have not only derived the Fokker-Planck equation for this specific situation of starting from some point, that same equation is what we need to solve if I start with some initial distribution of states and I want to see how the distribution evolves, okay? And the obvious thing to remember is that because this is just a Green's function, so I can use it to construct the solution to any other initial distribution. Okay, so that's the first point I wanted to make. Actually, second point. So first point is that this problem has boundary conditions which are problem dependent, okay, that you have to impose based on your understanding of the problem. But the initial condition is fixed for the condition distribution. However, if you think now about the distribution just of states at some time t, right, without being conditioned, you solve the same equation. Now you set the initial condition. So now the initial condition is freed because it's not the condition distribution anymore. Once again, you put the same boundary conditions. Okay? And from PDE theory, this is just using Green's function to construct the general solution. Okay, so that's the second thing. Now, the other thing I want you to think about is when we see this, we think immediately of advection diffusion type behavior, right? But our usual intuition is for the problem where A and B are constant. That's when we think, okay, that this diffusion term will just cause things to spread symmetrically and any asymmetric drift will come from A. That's our usual picture. But this is only true when A and B are constant. When they are not constant and you can give some arbitrary dependence on X, it can be very strange. Right? It need not be, this itself can give you something completely asymmetric. Right? All you have to do is make the diffusion higher for larger X and small for small x, and it will do something strange. Okay? So in what sense is this diffusive, or why is it, we would always call it diffusion, okay? Is because it's always true that it does simple diffusion type evolution locally. So that's particularly easy to see in this context, right, for this problem, because if I now consider the evolution of this equation for small time, right, I'm starting with a Dirac delta, so all my particles are at y, and if I evolve only for small time, they'll stay close to that y. Right? I mean, of course, I can solve it. I know it will be a Gaussian. Right? Why? Because if I am close to the initial y, I can approximate this a and b, which are general functions of x, by their values at y. Okay, so in other words, right, equation 1 gives advection plus Brownian motion, right, or Brownian diffusion. I should say always, okay. It can, of course, give it for the special case of A and B being constant, but it always gives advection and Brownian motion for a small right, time. Right, because then I can replace the general A of x by A at y, right? And this y is a constant here, so then you will just get the nice symmetric spreading. Okay, but that's only for initial time. And this argument I can use at any later time also. So let's say the stuff is evolving, or you think about this thing, the whole distribution is evolving. If I look at it at some region, and for a little time around that zone, I will see something that looks like classic advection diffusion. But then if I look at it over global long time scales, anything can happen. And this is entirely consistent with what we, I mean, in fact, that's a consequence of our initial assumption. Right? So remember when we started deriving the equation, we made 3 assumptions, the second and third of which was on the drift and on the first moment and second moment of the step. And there we said those are A and B, where A and B are some general functions of where I am. But already you can see there that locally they could be constant. Okay, so it's important to remember this, that so when you think Fokker-Planck equation doesn't mean that all my stochastic processes are just going to be very nicely diffusing in a very boring way. Right? It can, the same equation can account for all kinds of complicated evolution. So if suppose you are looking at some experiment and you see particles, and then instead of symmetrically, if they symmetrically diffuse slowly and the ball glows like root T, then you know it is diffusion. This is what we already discussed. But suppose you see it again and it's spreading, but it's not spreading symmetrically, right? It's spreading and then this part is spreading much more. Then you should not think, oh, this cannot be described by Fokker-Planck equation. It can, of course, still be described. Only question is, what is the dependence of B on X? And that's some information that will come out of the physics of the problem that you have to specify. Okay, but that process will also be governed by the same equation. Okay, so that's the important thing I wanted to keep in mind. Right? So this in fact covers a whole class of continuous stochastic processes, with the caveat that whatever, so in terms of particle trajectories, right, that whatever you're looking at is not interacting with other particles. So if you want in the ultra dilute regime where there are no particle-particle interactions, then for any kind of problem this will hold, okay, in some suitably generalized way. So this is only one dimension. You can have higher dimension problems, that can always be done. Okay, but why did I make the comment about this particle-particle interaction? So think of a situation where again I have many particles diffusing around, but now it's quite concentrated. Okay? So in such a system, the easiest, simplest interaction is that the diffusion coefficient becomes dependent on the concentration or the local density. Right? So if I'm in some local spot, the concentration is very high, then I'm not able to diffuse freely. Some place where the concentration is low, I'm diffusing as if I'm all alone. Right? So the diffusion coefficient can be a function of the concentration in this kind of problem. So if I think about it here, it would be like saying, okay, my probability of taking a step now is changed because I'm surrounded by many other guys. Right? And that's just to build intuition, but you can have all kinds of other situations. Right? It could be that for some other reason, your transition step probabilities now depend on how likely you are to be there, right? How many other particles are there. It could also be a consequence of what are called mean field interactions. So you can say that you think about birds. Okay, so when birds are moving around, then the advection term is important, right? So they are flying, and what is the probability of them flying in a particular direction? Right? This is how we model it because you don't know what the bird is thinking. But they typically have some alignment behavior. So if they are flying in a flock and they are surrounded by birds, right? If all the birds are in a certain direction, they have a high probability of going in that same direction. So if you want to model this kind of behavior, you would have to say that A depends not on X now, but on P itself. Right? Because what you're saying is that my probability of flying in a certain direction is somehow dependent on what is the mean direction of flying in my neighborhood. But how will you calculate the mean? You'll have to integrate over the probability of having a particular orientation. Right? So the mean is itself an integral of P. So in those kinds of problems, A depends on P. And when that happens, this is no longer a linear equation. Okay? It becomes a nonlinear equation. So you can get a nonlinear, okay, equation, right, when there are interactions. Okay, this is beyond the scope of the course, but I just want to point this out. Okay, so flocking systems are an example, right? Concentrated systems are an example. Other kinds of statistical mechanical problems where what is happening here depends on all its neighbors, right? All these problems can give you this kind of drift and diffusion coefficients that depend on the distribution itself. In other words, a nonlinear equation. Okay. And for such problems, right, are much easier to study via an SD. Okay, because first of all you have to derive this kind of thing. So I made exactly this flocking problem, right? I'm saying there's a bird. Now it's easy to specify a rule for choosing its direction of flying if you're evolving an individual bird. So you say, okay, I'm a bird, I have a certain velocity. I figure out some scheme to choose my velocity in the next time step, right? So I can just look at all my neighbors. I can do some kind of average, or I can choose the closest neighbor or whatever scheme you want, and you can update your flying direction. Okay? So it's very easy to come up with individual Bayes rules for such kind of complex problems, and then you simulate all of them, you see what they do. Okay? So that's just a trajectory approach, or in general, it's like solving an SD, because you'll also have some randomness in choosing the direction, etc. Okay, so in other words, this is also what's called an agent-based, right, model. Right? Where you're simulating, so agent here is just a generic term to mean it could be a particle, it could be a bird, etc. So these ABMs are the popular nomenclature in fields like social sciences, biology, economics, etc. But these are very useful because trying to write down the Fokker-Planck equation is going to be hard, because it's hard to translate this individual Bayes rule to something like this. Right? You'll probably have to make some kind of approximation to have it, to even write down the equation. Okay? And even after you write it down, if it's some nonlinear high-dimensional PD, here I'm doing it in 1D. Right? But even if you take the bird, it will have many variables, 3 space variables, 3 velocity variables, orientation variables. So the space will blow up. This x will become a vector, very high dimension. And it will be nonlinear. So there's no chance of solving this kind of PD, right, in any practical way. And then, of course, if you have many birds, then you have to have many, that will again increase the space. So this approach becomes untenable. Then people do these agent-based models. But what I want you to bear in mind is that there is a connection, right? This connection still exists. And the manifestation of such kind of complex interactions is that the Fokker-Planck equation will become nonlinear. And therefore, you cannot then do this kind of superposition. Right? So you cannot understand how the whole flock will behave by putting all birds at one point and getting one evolution this way. You really have to, each new distribution of birds will do something new. You have to simulate it and see. Whereas if the problem is linear, just one calculation of this thing will give you all other possibilities, okay, because it's linear. Yes?
And will depend on T, and if they can it be solvable by Fokker-Planck, or will still need SD?
Okay, so the question is, can these coefficients depend on time? And the answer is yes, and it changes nothing, right? It still remains a linear equation. There's no problem. So I can do the same thing. Yeah.
How will we account interactions in SD? Particle-particle interaction in SD?
Yeah, so we'll look, so SD, so you think of it like an ODE with noise for now, because you've not done it yet. So then you can just add some rule, right, to, I mean, you're doing an individual bird. So it doesn't have to necessarily be formulated within a classical SD. You could have some if-else condition or something. I mean, in the end, it's some simulation. You're simulating a bird. You have some way of updating its velocity, its position, its orientation, and then you solve an equation for its position. So you solve dx dt is equal to v, and v maybe adjusts according to some rule. So you can always do this. So I said SD here in the context of particles. It doesn't even have to be an SD. It could just be some kind of procedure to update things. It could be written as a difference equation also. It's fine. But the point is that you can directly formulate things for individual agents or particles very easily, which you cannot get this equation. That's why one always needs to have both these pictures in mind. But even when you're doing that, it's helpful to think about whether the distribution is somehow linear or not, right? Which is different from whether the equation SD is nonlinear or not. That's a separate question. And that's where it's good to have this picture also in mind. Okay, so that's what I wanted to say about this Fokker-Planck equation. Okay, so if there are no further questions on this, what we'll do next is consider an interesting twist on this Fokker-Planck. Which is to look at the backward version of the problem. Okay, so the idea here is I want to now, instead of looking at an evolution equation forward in time, right, okay, I'm starting at y, and I want to see how my probability of being at some position x at future time evolves. I rather say that I know right now that I have a particle located at x. Okay, so let's say I know that at some time I have a particle located at x. I want to see where it came from. Okay, so in other words, I switched what I know. Right? So in the previous problem, I'm saying I know where the particle was at t prime. I want to see the distribution of its possible positions at some future time t. Now I'm flipping it. I'm saying I know that there is a particle at position x at time t. Where did it come from? And because the problem is stochastic, that itself will be probabilistic. Right? There could be many different places that I originated to be able to come at this position. Right? Because it's stochastic. Think again about trajectories. So I started a given position, trajectories will go all over. Now I'm saying, okay, now I know I'm here. Where did I come from? It could have come from there, it could have come from there, because all trajectories are stochastic. So I want to find the evolution of the backward problem. That's what I mean by backward Fokker plan. In other words, if I'm looking for a evolution equation, it will involve the time derivative with respect to t prime. I want to find an equation for this time derivative. So just like the starting point of the forward was to consider the time derivative, there we of course began with expectation, right? But the forward time derivative in terms of t. Now I'm looking at, it's still the forward time derivative, but of the originating time, t prime. Okay, I want to do this because I can always begin with t prime equal to t. That will be my starting point where I'll have a Dirac delta, and then evolve t time backward. Okay, that's the idea. That's what will give me this understanding of where I have come from. So such problems have many applications, right? They're called source apportionment problems. The most typical example is in problems of pollution, spreading and so on. So if you know that, okay, your house is at a certain position, right? And you want to figure out, okay, what are the possible sources from which I can get, like, I don't know, high amount of some toxic gas, right, at some time. So let's say I'm saying there's a time window of 15 minutes, right? Then in 15 minutes, from where all can some pollutant arrive at a particular location? Or if you have done some measurement, right, and you're seeing that there's a river, and in the river you're measuring some pollution at some location, you want to know where this stuff came from, right? And of course nobody wants to confess that they are the ones who spilled it. But if you know that there's a certain time interval in which it has arrived, because maybe beyond that time interval the pollutant will degrade, right? So by measuring the concentration, you know, okay, at max it could have spent some time delta t in the river. So where did it come from? So if it's just an advection problem, it's trivial, right? You know the velocity of the river, you just do v delta t backward and you will find the distance. Okay, but most problems are not like this. You have some amount of diffusion or randomness. So then you will have not just a particular upstream location of the river where it must have come, but some distribution of locations with different probabilities. Okay, so this is the question. So there are many applications, including, I mean, the usual problem, like Delhi's pollution, where did it come from? This is a big thing. There was some report from IIT Kanpur a few years back which tried to look at this. So that's again a source apportionment. Right? So did it come from burning fields? Did it come from the city itself, from surrounding industrial areas, etc.? Okay, so this is the motivation of this kind of question. Okay, so let's see what we can do. Now here we will proceed directly by taking the time derivative definition on the distribution itself, and we'll see that we'll be able to make progress here in a way we couldn't in the forward problem. The forward problem, we had to consider the evolution of an expectation. Right? We didn't try to directly take the derivative, right? Because there it would not work. Here we'll see that it works, and when we see why it works, we'll understand that it would not have worked in the forward problem. Okay, so let's do that. So this is nothing but taking the limit of okay, so I applied the dt now is on t prime. Okay. And now what we want to do, just like before, is to use the Chapman-Kolmogorov, right, equation and introduce a mid-step, right? Because ultimately our goal is to do a Taylor series on P, right? So right now x and y are arbitrarily far apart because t prime and t are arbitrarily far. I want to introduce a substep which is close to y in this case. Right? Earlier I wanted to do close to x. Now x is fixed. Right? Remember, x is not a variable, x is fixed. Right? I know that it's at x at time t. It's the distribution over y that I'm interested in the past. So I want to introduce a substep that is close to y. Right? And this allows me to do it, right? Because I want to translate this to something at t prime plus delta t. And yes. Okay, so what I'm doing here is I'm going from T prime to T, but I can do it via an intermediate step, which is nothing but this T prime plus delta T, right? Because say T prime is here, right? T is there, and T prime plus delta T is in between. Okay, so I can use Chapman-Kolmogorov to go from T prime to T prime plus delta T at some Z, and then from Z to x comma T. Okay, so let's do that. Okay, I'll come to this thing later. So I'm reaching x comma T, but now from an intermediate location. Okay, so from y comma T prime, I'm going to Z T prime plus delta T, and then I'm taking the next step. So this is just the Markov chain, and I have to integrate over the intermediate step, dz. Okay, so this is the same step I had done the forward thing, but now I'm doing it in the y T prime, okay, in terms of where I'm coming from. Is that clear? So that's just Chapman-Kolmogorov now. Okay, now what do I do with this? Okay, so if you look carefully, this has the ingredients for me to do the Taylor series, right? Because y and z are now close. Okay, because they are at the same time T prime plus delta T. So in other words, I have required y and z to be close, right? Because I've done it through some z, and then when I take the integral, I'm going to say y and z as a usual thing, right? That y and z, the step is small. Okay. But how can I do this? Because you see that I have this extra term here. Right? So, but if you think about now what this term is, let's look at integral p of z t prime plus delta t etc. dz. I'm integrating over z, right? So it's like saying the probability of starting at y t prime and going to some z, integrating over all possible z, that is just 1. Okay, so I can multiply that whole thing with this, okay, and I can write it as right, because this integral is 1. So it's like multiplying it by 1, right? That's the idea. Okay. And now I can take this out common, right? So it's one integral. I can take this probability of going from y to z is common in both. I can pull it out, and I'll get a difference of these two guys, right? Right, so this part is common, and then I have a difference of this. and dz. Okay, now what I can do is I can Taylor expand z about y. Right, so it's the, so I'll just, all that is the same, I'm just writing it, right? So it's this probability where z, instead of z I have y, right? Plus z minus y, the derivative with y. Okay, plus the high order terms. And I can now substitute that just like before here. Okay. So what I've done now, the difference from before is instead of Taylor expanding the variable which is where I am going to go, I'm Taylor expanding where I have come from, right? And that I can always do, right? This is just some function. In the end, this is a smooth function of both x and y. So I can Taylor expand here as well. It's just some function. So I can always write this down because it's the PDF is a smooth function. Then after writing that down and I substitute to be able to use my assumptions about the moments, now I have to only be doing forward step. Right? Because remember my assumption was that, for example, the first moment of going from y, for taking a forward step is A. Second moment of the forward step is B. Right? Not about stepping backward or where of having small differences in my starting point. That was not part of my assumption. Right? But here you see we are fine because look at what I'm doing the integral over. Right? I'm doing the integral over z. So when I substitute for this difference with the Taylor series, right, this term will be there. Okay, no problem. Then here I'll have this z minus y. This is the first moment, right? So this will come out as a constant. It's only a function of y. And I'll have z minus y integral over dz and the probability of going from y to z. So that's exactly the first moment. Okay, so that's why this keeping this constant was important. So this is the probability of taking a forward step, and z minus y gives me the first moment. This will give me the second moment. Okay, so when I substitute back here, I'll directly get dp by dy times a, and d square p dy square by times b by 2. And of course, this p of y will cancel with this because it's a difference, right? So this will cancel with this term, and then I'll have minus of those two guys, and they will give me a and b. So finally, I'll skip the details. It's exactly the same as before. So I'll get the final equation, derivative in t prime, right, of this quantity. Given that I'm at x comma t now, right, where did I come from? Right, that time derivative on the t prime is equal to, now I have minus, right? And you see a is not inside now, right, because a is sitting outside here directly. Last time a went inside the derivative because I had to do integration by parts. Right? So now a is outside. Is that okay? So we finally arrive now at an equation that says what is the time derivative of on the t prime. So it's like saying I know I'm at a certain position now. I came from t prime, but how will that distribution of coming from t prime to get here change if I start varying the t prime? Okay, that's what I want. So because then I can take my t prime to begin at t, and then I can make it go backward, right? So as I know now that when t prime is equal to t, this is just a Dirac delta as before, because I know I'm here and t prime is equal to t. As I take t prime backward from t, then the distribution will evolve away from the Dirac delta, okay? And that will tell me what is the probability of coming to x, right, from an earlier time t prime, right, at what y's have I come from? What is the probability of coming to x from a certain y, right, as t prime goes further and further back. Okay. Now, but however, to understand it fully, we cannot do this because this t prime is not going back, right? This is the forward derivative on t prime. And what I'm saying is I want to go backward, otherwise it doesn't make sense. Right? What I really want to do is to take t prime backward. So an easy way to see the equation where I can just, I transform my variable, so I have a new time variable tau whose increase means I'm going backward. Okay, so to do that, I'll say, right, just transform the time t okay. So I'm going to write t prime as t minus some time tau, and now as tau increases, the t prime will go backward, right? And when tau is 0, t prime is equal to t. So if I substitute that in here, I'll get the equation for dou by dou tau now, okay? But I know, of course, that dt prime minus d tau, right? So if I do this, I'm suppressing this, but it's the same thing. You just change t prime to tau, okay? So this now I'll have d by d tau of t. There's a minus sign that's going to come here and go on the other side, right? That will make this plus and this plus. And when I pull it on the other side to get the usual advection diffusion equation, or if you want, let me write it like this. Right? Or if you want, if I take it to the other side, I'll have minus is equal to this. So now this equation will tell me how the distribution will evolve as I go backward in time, which means as tau increases. Okay? So I can solve it in the usual way, but it will give me the information I want. And its initial condition, of course, is that t at tau equal to 0 is the Dirac delta, right? So only when y is at x, I will have a distribution, and then as tau increases, I'll get a distribution over y. Okay, now I just realized now that maybe in the beginning of the lecture when I wrote the Fokker-Planck equation, the a was on the other side, okay, and that a should have a minus sign. I think I didn't write the minus sign. Okay, so for the video at the beginning of the lecture, I had written the Fokker-Planck equation for the forward problem as dp by dt is equal to, it should be equal to minus minus d by dy ap and plus 1 by 2 d square dy square bp. It's there on top. Oh, I did put a minus. Okay, I'm wiser than I thought. So if you look on top, I have, let's just look at it again. So for the video, you see this equation now. This is the backward Fokker-Planck, okay? Okay, and you contrast it, so keep that in your mind now and just contrast it with the forward one. Okay, this is the forward Fokker-Planck. Okay, so if I were to rewrite this the way I wrote that, right, I would say plus, right, is equal to this. So now this forward equation is the standard advection diffusion type equation. Of course, the coefficients are inside. But if you contrast this with what we derived for the backward thing, first thing is that the A's and the B has come out. Okay, so that means if A and B are constant, it doesn't matter. But if they are not constant and dependent on X, this is of course different from having the A outside. Okay, that's the first thing. But for now, let us think about constant A and B. So normal Brownian motion. So you have particles moving, right? Normal Brownian motion. This is like a normal constant velocity. Okay. So what is happening, interestingly, is you imagine there's a particle, think only of drift velocity now, right? So I have a particle is moving with constant velocity. And I know that, okay, it's at this position at some time. Where did it come from 2 seconds back? I just have to go backward with the same velocity, right, to find where it came from. So if I have purely advection, it's a trivial problem, constant advection. I just have to go backward. In other words, when I solve the backward equation, the velocity should flip sign, right? Instead of the Dirac, so if I start with Dirac delta, I have only velocity, the Dirac delta will shift. To go backward, I have to make the Dirac delta move backward. So the A should flip sign. But you notice the B is plus on the RHS, and that stays plus. Okay. So according to intuition, the advection term has the same A but with the reverse sign. So when I go forward in the forward focal length, I just come backward. So if I know I'm here at a certain time, where did I come from? I just have to take myself backward, right? Evolve with minus A instead of plus A. But you see, B doesn't change sign. I'm not doing negative diffusion. Okay, and that makes sense because I'm saying I know I'm here, I'm a Dirac delta. Where did I come from? That should spread out. Right? And it spreads out with the same diffusion coefficient if B is constant. Right? So the same stochastic Brownian motion which causes me in the forward time to spread out is also the reason why if I try to backtrack, I will have to spread out. Because where I'm coming from starts spreading out, right? Because there can be different locations. The further I go back, more is the spread, right? Because there could be further locations that have diffused to my current point. And that diffusion or that spreading out of that ball of probability in forward and backward will be the same, right? Because the B is the same, provided it is constant. Right? If it's a function of space, then you see the behavior is going to be different. Okay, so if I think of pure diffusion, the Dirac delta will spread like a Gaussian in identical ways. Whether I'm asking the question, where am I going in the future or where I have come from, right? And as I go backward in time. Except if the B is dependent on space, then you can see there will be a subtle difference. Okay, but this is a nice idea to keep in mind. It kind of reinforces what we are working with, right? Stochastic processes. And this is now very different from the mass transport problem, just concentration, advection, diffusion problem, right? This is where there's a clear difference between thinking about P and an actual concentration field. Because and the usual mass transfer diffusion problem. Because there, if I do backward in time, I will actually do negative diffusion. Right? Because suppose I start with a bath, right? I put a drop of dye and I watch it spreading. Then I freeze and I say, okay, what was the shape of the initial drop? I have to rewind the movie. Okay, this is an ill-posed problem, that's fine. But in principle, what I have to do is actually go backward in time. So instead of spreading out, I have to contract. Right? So I'd have to solve the equation with a negative diffusion coefficient. In other words, if I replace T by minus T, I'll get a minus sign, the velocity will flip sign, and the diffusion will flip sign. Okay, so instead of spreading, I'll have to contract. And of course, negative diffusion is numerically unstable. That's why we cannot solve such problems easily. Right? These are called ill-posed inverse problems. But that is what would happen in a mass transfer situation. This backward focal length is a different thing. Right? You see, so it's a completely different question. Right? I'm saying I know that I'm here, and where are all the locations from which I have come. That problem is also with a positive diffusion. I'm still spreading because my probability of where I've come from is also spreading. Okay, so that's a subtle difference. So backward focal length doesn't mean solve forward focal length backward in time. It's not the same. Okay, so we'll not really look at this much in this course, but it's a nice way to complete our discussion of focal length, right? And it again reinforces the importance of thinking about stochastic processes both ways, in terms of trajectory and in terms of distribution. Okay. Any questions? So homework exercise which you could try is, you see now we did this derivation by directly taking the definition of the time derivative on P. You could try doing the same thing for the forward focal length, but you'll see then that this trick will not work. Okay. The reason it works here is because we're doing the integral over z, and z is the variable to where I am going. But if you try the same trick in the forward, the z would be sitting where I've come from, and integrating over where I've come from will not give you 1. It's only integrating over where I have gone to in the forward step, that gives you 1. So this trick doesn't work if you try to do it in the derivation of the forward Fokker-Planck. So there I have to consider the expectation, okay, and how it evolves. But here, because of this, we can directly do this. Okay. Okay, so now to end our discussion of these things, what I want to do is consider to use the forward Fokker-Planck equation and learn something about the behavior of Brownian motion. Okay, so let's now consider classic Brownian motion. Okay, which is what Einstein considered. So we don't have any advection. We just have pure diffusion, right? Which is a consequence of these small uncorrelated steps. So in terms of this Fokker-Planck equation, it's going to be, we're going to define a Weiner process after the probabilist Weiner, right? And it's going to be this process that is governed by the Fokker-Planck equation, where A is equal to 0 and B is a constant. We can set it to be 1. Okay, so then you will have just that simple diffusion equation. And now so the Weiner process is, traditionally, the trajectories of this process are given the notation capital W. Okay, so let's take a Brownian walk. So you start here, and W is how the position of the particle evolves in time. Okay, and each trajectory is a different realization of this capital W of t. But now if I do many such trajectories, I can always look at the distribution small p over W, right? So if I use capital W for the trajectories, I should use small w, right, for the space, right, given that I'm at W naught at T naught, let's say. Right, this would be the condition distribution, which is governed by the Fokker-Planck equation with B equal to 1, A equal to 0. So this we are going to define as the Weiner process, which corresponds to just a simple diffusive motion. And now, because I know the equation for P, I can immediately examine some properties of the trajectories of W. And this is useful when we are going to look at our stochastic differential equation for the same process. Right? So now that we have done the Fokker-Planck nicely, we can use that to define what is Brownian motion, which is just B equal to 1, A equal to 0, and that the derivation for this case is the formalized version of Einstein's derivation. So we'll have a clear understanding of what happens here. For example, you can start with this Dirac delta, and then you'll see it will just evolve like a Gaussian. Right? That is a simple diffusive motion, etc. But if I want to look at trajectories of W, I'll have to solve a stochastic differential equation for the position of individual particles. And what I would like to know is what kind of trajectories are these, right? We'll have to deal with situations of, are these trajectories continuous in time? Are they differentiable? If they're not differentiable, how can I write an ODE for the evolution of W in time? Right? These are the issues we'll have to wrestle with. So we can already get some insight into the behavior of individual trajectories of W and their kind of noisy character using this distribution. Okay. So the first point is to look at increments. Right, delta W in the trajectory. So I have many trajectories. I take a small time step delta t. Right. So if I'm looking at many trajectories over a small time step delta t, I'll get different increments delta W. In other words, I'll get a distribution of increments. Right. This is what, in fact, what Einstein started with. What is the distribution of steps? And here I can find the distribution of steps directly because I know the Fokker-Planck equation. Right. It's like considering the equation for P where omega is omega naught plus delta omega. Or in other words, you solve the Fokker-Planck equation for a small time interval. and I already know the solution. Remember, I start with a Dirac delta at omega naught, and I look at what happens forward in time, right, for delta omega. And what is the solution? Solution to diffusion equation for a pulse is just a Gaussian. Okay, so the PDF of delta W, right, is just going to be equal to, is just a solution of the Gaussian, right? We already wrote this solution, remember earlier when we looked at Einstein's derivation. Right, or if you want right, where of course so I want to find the distribution of the steps delta W on all my trajectories, right? So if I simulate many trajectories somehow, right, I'm looking at many of them. At any instant of time, I look at one time step delta t, I'll get a whole distribution of steps. What is the distribution? Right? Because I've defined the process this way, a process that follows this Fokker-Planck equation will have exactly this distribution of steps. Right? I've just written it here to emphasize that I've got it from solving the Fokker-Planck. So this is just delta W. So in other words, the distribution of steps will be a Gaussian, right, whose variance goes like root delta t, right? This is the, the variance goes like delta t, the standard deviation is like root delta t.
So is that 2 delta t?
Yeah, 2, sorry. Okay, so in other words, if delta t is small, the variance gets smaller and smaller. The larger the delta t I take, the variance of the distribution spreads, right? So more probability of taking bigger steps. And the important thing is that the standard deviation of my, or the mean step, the root mean square step grows like root delta t. That's exactly the diffusive process. Okay, so that's one check, but what I want you to realize here, which is going to be of qualitative importance, is that the increments are all independent. In other words, the step I take now and a future step, these are statistically independent. Why? Because the distribution of steps only depends on the step size and on delta t. It doesn't depend on W separately. In other words, it doesn't depend where I am in space now. It doesn't depend on what I've done before. Right? It's only a function of the step size itself. Okay. So this tells us that okay, this is what in fact Einstein started with, right? We said, okay, I have the Brownian motion at any small time interval, it takes a step, and this step is completely uncorrelated from its previous step or where it is located now or how much time has elapsed, right? It's just a random, it's like tossing a coin. And that's exactly what this is telling you, right? If I want to make another step, I just have to sample this Gaussian distribution and I sample the same distribution each time. It doesn't matter whether my previous step was big or small, the probability of taking the next step has the same distribution. Okay? So this just emphasizes, of course, what we already, it's all built into the Fokker-Planck, but I'm just showing it to you explicitly. Okay? So if I was to use the Fokker-Planck equation as a way to define the Weiner process, which is what I'm doing, I can infer that the trajectories of those processes, of that process, will have increments that are statistically independent, which is good. Right? This is what I want random walk to be like. So that is a tick mark for this Weiner process being a representation of random walk, that its increments are statistically independent. Okay, that's the first. Okay. Now the second question I can ask is are these trajectories continuous in time? Okay, so they are statistically independent. Now question is, so if I look at these trajectories, W of t, right, are they continuous functions of time? Or do I take am I teleporting? Am I making big jumps? Right? Or am I always arbitrarily close to where I was at the previous time? Now we know that it should be continuous. Why? Because it's this process that's coming out of the Fokker-Planck equation, which is valid only for continuous stochastic processes. That's what we started with. Right? To derive the Fokker-Planck equation, we had to assume that Lindbergh condition holds. Right? So it should be, it has to be continuous. But we can easily show it from the Fokker-Planck equation, just like a consistency or sanity check, and that will help us in the next step. Okay? So remember that to check whether it's continuous, I need to see right, I want to find what is this probability. Right, and for a continuous process, this probability should go to 0. Okay. And I want to find it for big steps. Okay, now the nice thing is I'm going to take the limit of delta t approaching 0, right? But remember, I'm asking for what is happening if epsilon is arbitrarily, I can choose epsilon however I want, right? Something non-zero. But now we know what P is as delta t goes to 0, right? It's given by its initial condition to the Fokker-Planck equation, because this P satisfies a Fokker-Planck. So then I can write this Okay, now what I've done here is not strictly correct. I'm just skipping some steps which you can show formally. But what I want you to see is, okay, this delta t is, we'll come to it in a second. But you see what will happen is, as I approach t going to t0, this p is going to look like a Dirac delta. Okay, and importantly, the Dirac delta will give you a contribution to the integral only if omega naught is part of the integration interval. But my epsilon is arbitrarily large. Okay, so I can